So today we're covering Chapter 5, Lesson 9, Complex Numbers. So what you're going to learn today is how to add and subtract complex numbers and how to multiply and divide complex numbers. So some of the vocabulary to keep in mind is what's an imaginary unit, what are pure imaginary numbers, what are complex numbers, what's an absolute value, and what are complex conjugates. So how do complex numbers apply to polynomial equations? So consider the equation 2x squared plus 2 equals 0. If you solve this equation for x squared, the result is x squared equals negative 1. Since there is no real number whose square is negative 1, the equation has no real solutions. French mathematician René Descartes, who was alive from 1596 to 1650, proposed that a number I be defined such that I squared equals negative 1. So this is where the imaginary unit comes in, right? So we're going to start to talk about the imaginary unit I. So adding and subtracting complex numbers. Since I is defined to have the property that I squared equals negative 1, then the number I is the principal square root of negative 1. That is, I equals the square root of negative 1. And so for a long time, we talked about how the square root of a negative number had no real solutions, right? There was no real number. Well, now we have a number. We have an imaginary number. We have an imaginary unit, I. I represents the square root of negative 1. So I is called the imaginary unit. Numbers of the form 3i or negative 5i and I radical 2 or square root of 2 are called pure imaginary numbers. Pure imaginary numbers are square roots of negative real numbers, right? So obviously 1 is a real number, but negative 1 is a negative real number. For any positive real number b, the square root of negative b squared is equal to the square root of b squared, or bi. So let's look at an example where this comes into play. So square roots of negative numbers. So if someone asks, hey, simplify the square root of negative 18, before we would say that there are no real numbers that work, but now we can use this imaginary unit here, okay? We're going to use I. So if I took the square root of negative 18, I could simplify that into the square root of negative 1 times 3 squared, right, which is 9, times 2. So if I factor this apart into negative 1 times 3 squared times 2, this would help me to simplify. Now, remember, the square root of negative 1 is I. The square root of 3 squared is 3, and then the square root of 2 is, wouldn't be able to be simplified any further, right? So the square root of negative 1 is I, the square root of 3 squared is 3, and the square root of 2 would just stay the square root of 2. And so when I simplify it, it would be 3i radical 2. Same thing here. If I have the square root of negative 125 x to the 5th, again, I'm going to go ahead and factor it apart. So I would have the square root of negative 1 times 5 squared times x to the 4th times 5x. So again, if I look at these individually, right, the square root of negative 1 is going to be I. The square root of 5 squared is going to be 5. The square root of x to the 4th is going to be x squared. And then the square root of 5x can't be simplified. So then when I rewrite this, it's going to be 5ix squared radical 5x. So this is a way that we can now simplify negative real numbers, right? Before we said there wasn't anything real. Well, now we have this imaginary unit that we can utilize to help us simplify these. So the commutative and associative properties of multiplication hold true for pure imaginary numbers as they do for real numbers. So let's look at an example here. So if we were to multiply pure imaginary numbers here, so negative 2i times 7i, okay? So these would multiply together just like real numbers. So negative 2I times 7I, well, I know negative 2 times 7 is negative 14, and I times I is I squared. Now, one thing to remember is I squared, right? I squared is equal to negative 1, right? Because if the square root of I is negative 1, well, if I took the square root of negative 1 times the square root of negative 1, that is just negative 1. And then negative 14 times negative 1 is positive 14. So these complex numbers here, when I multiply them together, actually give me a real number. Let's look at b now. If I took the square root of negative 10 times the square root of negative 15, right? So the square root of negative 10 is I square root of 10, right? Because that would be the square root of negative 1 times the square root of 10. So that would be I square root of 10. Same thing with the square root of negative 15. That would be I square root of 15. And then I can go ahead and multiply them together. So I times I is I squared, and the square root of 10 times the square root of 15 is the square root of 150. And then I can continue to simplify. I know these I squared is going to be negative 1. And then the square root of 150 can actually be simplified to the square root of 25 times the square root of 6. And I recognize 25 to be a perfect square, so that could be simplified into 5. So it would be negative 5 square root of 6. You can also use the properties of powers to help you simplify powers of I. So for example, if I said I have I to the first power, that's just equal to I. If I had I to the second power, well, that's the square root of 1 times the square root of 1. And so that would be equal to negative 1. So whenever I have I squared, that's actually negative 1. And that's something we already illustrated in previous examples, right? Because these two multiplied together just give me negative 1. If I have I to the third, then that would be like square root of negative 1 times square root of negative 1 times square root of negative 1, right? Which equals negative 1i, because square root of negative 1 times square root of negative 1 is negative 1. And then negative 1 times I is negative I. If I do I to the fourth, that's going to be the square root of negative 1 times the square root of negative 1 times the square root of negative 1 times the square root of negative 1. So if I were to simplify this, I know that the square root of negative 1 times the square root of negative 1 is negative 1. And the square root of negative 1 times the square root of negative 1 is also negative 1, right? So whenever I see a pair of radical negative 1s being multiplied together, I know that's just going to give me negative 1. And so since I have two pairs there, I have a pair of negative 1s multiplied together. Negative 1 times negative 1 is positive 1. And if I did I to the fifth, same thing. I have, excuse me. Excuse me. I have, again, two pairs of square root of negative 1s multiplied together. And then I have a fifth one here, so that would be negative 1 times negative 1 times I. Well, negative 1 times negative 1 is positive 1 times I is positive I. If I do I to the sixth, again, there are my pairs there, so that's going to be a negative 1, negative 1, negative 1. So negative 1 times negative 1 times negative 1 is negative 1. And if I do I to the seventh, same thing. I see I have three pairs with an extra square root of negative 1 there, so that's going to be negative 1 times negative 1 times negative 1 times I, which would be negative I. And if I did I to the eighth, same thing. I see four pairs of negative 1, so it'd be negative 1 times negative 1 times negative 1 times negative 1, which when I multiply that all together is just positive 1. And so really the pattern we want to see is whenever we have the first power, it's I, negative 1, negative I, positive 1. Then it's, if you notice, every fourth one, it just cycles back around. I, negative 1, negative I, positive 1. So basically, every fourth power of I is just equal to 1, right? So if I go to I to the eighth, that's equal to 1. So if I went to I to the 12th, that would also be equal to 1. I to the 16th would also be equal to 1, right? Because all that ends up happening is you have these pairs of square root of 1 that ends up just giving you negative 1. And if you have an even number of pairs, that gives you a positive 1. If you have an odd number of pairs, that gives you a negative 1, if you have an extra square root of negative 1 left over, that's going to make it an I. So sometimes you have negative I, sometimes you have positive I. But basically, this is the pattern, right? So this pattern will follow along. So let's look at an example where this plays out. So if I have I to the 45th power, right? I know that I can factor it apart into I times I to the 44th, because that's like I to the first, right? I would add their exponents and that would equal to that. But what I notice here is I have a factor of 44, right? The exponent, right? So if it's I to the 44th power, that's going to just cycle through those powers of 4 11 times. So I know this I to the 44th is really just going to be negative 1 to the 22nd power, right? Because that's I squared there. And so negative 1 to the 22nd power is just going to give me positive 1. And again, this I was just hanging out here the whole time. And then I times 1 is just I. So this would be the I to the 45th power can actually just be simplified into I. Again, we could have listed out all the powers from 1 all the way down to 45, and you would just see it cycle through that same pattern of 4 all the way down. So the solutions of some equations involve pure imaginary numbers. So here we have 3x squared plus 48 equals 0. So if we were to go ahead and solve this, right, we have our original equation. We would go ahead and subtract 48 from both sides. So we have 3x squared equals negative 48. And then we would go ahead and divide both sides by 3, and that would give us x squared equals negative 16. And then we would go ahead and take the square root of both sides, right? So the square root of x would give me both the positive and negative of the square root of negative 16, right? So this is a place where we would get stuck previously, because we would say, oh, this doesn't have a real solution. But now, since we have imaginary numbers, we can come up with the imaginary solution. So again, simplifying the square root of negative 16. Well, that could just be broken up into the square root of negative 1 times the square root of 16. And I know the square root of negative 1 is I, and the square root of 16 is 4. So this would simplify into x equals plus or minus 4i. Because now with imaginary units, we can simplify negative square roots. Consider an expression such as 5 plus 2i. Since 5 is a real number and 2i is a pure imaginary number, the terms are not like terms and cannot be combined, right? I can't combine 5 plus 2i. This type of expression is called a complex number. So if I look at this, this would be similar to if I said, hey, what's 5 plus 2x? You wouldn't be able to combine those together because they're not like terms. Same thing with imaginary numbers, right? A real number and an imaginary number can't be actually combined together, but it's still considered together a complex number. So a complex number is any number that can be written in the form of a plus bi, where a and b are real numbers and I is the imaginary unit. A is called the real part because it's just a real number, so it's got no imaginary part attached to it. And b is called the imaginary unit because it has an I attached to it, right? So an example of a complex number would be 7 plus 4i, and 2 minus 6i would also be an imaginary or a complex number, right? That's the real part and that's the imaginary part. So the real part here is 7, the imaginary part is 4i. Here the real part is 2, the imaginary part is minus 6i. And here they just wrote it as, you could write it as minus 6i or plus negative 6i. Either way it means the same thing. So this Venn diagram at the right shows the complex number system. If b equals 0, the complex number is a real number. If b doesn't equal 0, the complex number is an imaginary number. And if a equals 0, the complex number is a pure imaginary number, right? So basically, if you have a real number plus an imaginary number, or pure imaginary number there, right? This would be a complex number. Well, if b is 0 and there's no imaginary unit to it, then it's just a real number, right? Because this part would just be 0, and 0 plus a real number is a real number. But if you had no real number with the imaginary number, right? If A was 0, then it would just be a pure imaginary number. It'd be like 4i or I or negative 3i, right? That's a pure imaginary number. The two complex numbers are equal if and only if their real parts are equal and their imaginary parts are equal. That is, a plus bi is equal to c plus di if and only if a equals c and b equals d. So if a is equal to c and b is equal to d, then these two complex numbers would be equal. So that sounds a lot harder than it actually is, but let's take a look. So if we were to equate complex numbers, it says find the values of x and y that make the equation 2x minus 3 plus quantity y minus 4i equal to 3 plus 2i true. So kind of what we said here is we have a complex number here, and we have a complex number here. Well, remember, this is the real part of the number. This is the imaginary part of the number. Here is the real part of the number. Here is the imaginary part of the number. So if I wanted to find out what values of x and y are going to make this equation true, well, we're going to set the real parts equal to each other, and we'll set the imaginary parts equal to each other. So the real part is 2x minus 3 here, and the real part is 3 here. So 2x minus 3 has to equal to 3, right? So 2x minus 3 has to equal to 3, the two real parts. And if I were to solve that, right, add 3 to both sides, you get 2x equals 6. Divide both sides by 2, x equals 3. So in order for this equation to be true, x must be 3, right? Because if it's 3, 2 times 3 is 6. 6 minus 3 is 3. So I'll have 3 here and 3 here. It'll be equal. So that's the real part. Now let's look at the imaginary part. I have y minus 4i has to equal to 2i, right? Here's the imaginary part. Here's the imaginary part. Set them to equal to each other. So again, I'm going to go ahead and solve. Add 4 to both sides. I get y equals 6. Again, if y is 6, 6 minus 4 is 2, so I'd have 2i there and 2i there. So these would be the values of x and y that I would need in order to make this equation true, in order for this complex number to be equal to this complex number. To add or subtract complex numbers, combine like terms. That is, combine the real parts and combine the imaginary parts. So here are two examples. So here it wants me to add and subtract these complex numbers. So simplify them, right? So I have 6 minus 4i plus 1 plus 3i. So again, complex number. Here's the real part. Here's the imaginary part. Here's the real part. Here's the imaginary part. So I'm going to go ahead and combine like terms, right? I can do 6 plus 1, and I can do negative 4i plus 3i. Well, 6 plus 1 is just 7, and negative 4 plus 3 is negative 1, so I have 7 minus 1i, or 7 minus I. And then let's take a look at the second one here. So again, the two real parts, the two imaginary parts, this time I'm subtracting. So it's going to be 3 minus 5 and negative 2 minus negative 4. And again, 3 minus 5 is 2, or negative 2. And negative 2 minus negative 4 is going to be positive 2. So I have negative 2 plus 2i. Again, the real part and the imaginary part. So multiplying and dividing complex numbers. Complex numbers are used with electricity. In a circuit with an alternating current, the voltage current and impedance or hindrance to a current can be represented by complex numbers. You can use the FOIL method to multiply complex numbers. So here's an example. It says multiplying complex numbers. Electricity. In an AC circuit, the voltage E and current I and the impedance Z are related by the formula E equals I times Z. Find the voltage in a circuit with a current 1 plus 3 J amps and the impedance 1 plus 5 J ohms. And really, these are I's here. If you imagine they're I's, even though they're listed as J's. All right, so I take my formula here, E equals I times Z, right? Where E is the voltage, I is the current, and Z is the impedance. So again, it says that my current is 1 plus 3i, and my impedance is 7 minus 5i. So again, if I were to multiply these together, so previously when I was just adding them, I could combine like terms, or if I was subtracting them, I could combine like terms. But when I'm multiplying them, it's just like multiplying two binomials together, right? I can use that FOIL method. I can do 1 times 7, 1 times negative 5i, 3j times 7, or 3i times 7, and 3i times negative 5i. So I'm going to go ahead and do that using my FOIL method, and then I can go ahead and simplify. So 1 times 7 is 7, 1 times negative 5i is negative 5i, 3i times 7 is 21i, and 3i times negative 5i is negative 15i squared. And so if we remember, the I squared is really just negative 1, right? So we can simplify that there, because I squared would just be radical 1 times radical, square root of negative 1 times the square root of negative 1, which is negative 1. And then we can simplify this a little further. I know that negative 15 times negative 1 is positive 15. And so then I would add that with 7, because I know 15 times plus 7 is 22. And so that would be my answer here. I know that the voltage would need to be 22 plus 16i. So that would be my final answer. Two complex numbers in the form of a plus bi and a minus bi are called complex conjugates. So we've talked about conjugates before when we were talking about radicals. Complex numbers also have conjugates, right? Whenever you have the same thing, but one is adding and one is subtracting, right? Those are conjugates of each other. So the product of complex conjugates is always a real number. So for example, 2 plus 3i times 2 minus 3i is equal to, again using the FOIL method, 4 minus 6i plus 6i plus 9. And if you notice, the two middle terms, the two I terms, will zero out, leaving you with just 4 plus 9, which is 13. So we can use the fact that we know that complex conjugates give us real numbers to simplify quotients, right? Division problems of two complex numbers. So let's look at some examples here. So I have two complex numbers being divided together, right? So I have 3i divided by 2 plus 4i. So again, I can use complex conjugates to simplify this. So again, the conjugate of 2 plus 4i would be 2 minus 4i. And I would have to make sure to multiply that on the top and bottom, right? Multiply the numerator and the denominator by that. And when I multiply that, right, 3i times 2 is 6i. 3i times negative 4i is negative 12i squared. And then when I multiply the two complex conjugates together down here, that's just going to give me 4, and the two middle terms would zero out, minus 16i squared. Remember that I squared is just negative 1, because that's the square root of I squared is just I, right? So then I would have 6i plus 12 over 20, right? Because this would just be 4. And then if that's negative 1, that's going to make that into positive 16. So that's going to be 20 there. And that would be my simplified answer here, right? In order to simplify complex numbers, you can't have a complex number in the denominator. That's why we use the conjugate. Let's look at B. So I have 5 plus I divided by 2i. Again, I'm going to go ahead and use complex conjugates here. Oh, I forgot about this part. Simplifying it into standard form. So typically we would put the real number first. So 12 over 20 simplifies into 3/5. And 6i over 20 simplifies into 3/10i. So this would be the standard form of it. So let's go ahead and look at B. So same thing, we're going to use the conjugate, right? But since there's no adding or subtracting, the conjugate is just 2i. So I, because all I needed to do is become I squared. So I'm going to multiply the numerator and the denominator by I. So 2i times I is 2i squared. And then 5 times I is 5i, and I times I is I squared. I squared just becomes 1. So that's going to give me 5i minus 1 up top. And then 2i squared, so I squared again is negative 1. So negative 1 times 2 is negative 2. So again, this would be the simplified version of it. Then again, I want to get into standard form. So -1 over -2 is positive 1/2, and 5i over -2 is -5 over 2i. So that just becomes simplifying a fraction. Again, you would write your I term second, and you write your real part first and your imaginary part second. That is the standard form. All right, thank you guys for watching. Let me know if you guys have any questions.